Alrighty, we are going to talk about rockets today. So, what do you know about rockets?
They go zoom.
The what?
They go zoom.
They go zoom. What do you know, Randy?
They're really, really fast, and a large portion of all the weight is fuel.
Okay, they go really fast and a large portion of the weight is fuel. What do you know, son?
Dr. LeBron built the V2 rocket.
Okay, we've seen about Werner von Braun. Well, the actual method that a rocket works, and you know what, I am pretty sure I have the slide in here with the quote that's fun. There it is, yeah. This is from an editorial that was published January 13, 1920 in the New York Times. And it quotes it here that says that Professor Goddard, with his chair in Clark College and the countenancing of the Smithsonian Institution, does not know the relation of action to reaction and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. So first of all, you guys should be a little dissed on that, ladled out in high schools while you're taking this in college. But what does he mean in this, this derision of Professor Goddard, for whom the Goddard Space Flight Center is named?
Apparently he's an idiot.
Well, what does it mean when it says the relation of action to reaction?
Newton's third law.
Newton's third law. He's saying that Professor Goddard doesn't understand Newton's third law. And what he has is a fundamental misunderstanding of what happens with a rocket. So going to what Randy said, a rocket is largely fuel. Why? Because the way a rocket works is it ejects fuel. It actually is absolutely obeying the action-reaction thing. You have fuel in the rocket. You throw the fuel out. You got the action of the rocket pushing on the fuel. What's the reaction? The fuel is pushing the rocket up as the rocket pushes the fuel down. And so it's absolutely relying on Newton's third law. What the person who wrote the editorial was thinking was that the rockets blow out material and it has no effect on the rocket until that material hits something. It's kind of like saying, if we were on ice and I throw a rock, conservation of momentum isn't going to make me go backward. That rock has to hit something and bounce off it before I go backward. Right? The person writing the editorial was the one that was missing the information ladled out daily in our high school classes. Now, oops, I had to hold it longer. Going back to this, a key then for the rocket is to make the direction at which the exhaust leaves the right direction. If you have a bomb, in general, the bomb is going to just have material blow out in 4 pi stare radians. How's that? In all directions. In which case, as the material blows out in all directions, the net force on whatever's at the center of the bomb is zero because you have just as much in all directions. If you do that with your rocket, if the rocket explodes, it's not going anywhere. So what you need is you need to make it so all the stuff you blow out is going one direction. So the basis of a rocket is you have a redox reaction, so you have a fuel and an oxidizer, and then you have your reaction occur there in what's called a combustion chamber, surprisingly enough. Now, if it's a solid rocket, the combustion chamber basically is the entire casing there of the rocket. And then you have that nozzle that will make the stuff that's ejected, it's coming from this hole, so it could go in any direction like that. If it comes like this, it's going to bounce off like that. It comes like this, it bounces off like that. So that you have, as much as possible, the direction of the fuel is pointing away from the direction you want the rocket to go. So you have the maximum forward force of the rocket. In the term of a rocket, we call that the thrust. Now, I have these two links here, and I already have them queued up. And so let's watch a little video of something with rocketry, but it's not, come on. It's not a standard rocket. It's something different. Just have some annoying music that's going to start up. A lot of build-up.
Why is this annoying music?
Because they go, fly!
Oh, sail?
You notice?
Huh?
You notice?
No. Yeah, it's called sail. This is a Oh, no way.
Look, they're dolphins.
Yeah.
Yeah, it's fun thinking too. So see, they connect the output of the jet to the hose. They're just blowing water into the hose from the jet ski. That's why the jet skis are involved. And yeah, they put gas in. That was important. I'm going to stop it here because we've seen enough. Okay, so in watching that, it's very cool, right? What are they doing here that's allowing them to do the flyboard thing? What's basically going on? Okay, there are some pressure aspects involved. What did you say? Propulsion.
They're just doing it. Well, I don't know how to say it. I know they're still more
It starts with the jet ski is blowing water really fast into their hose. Now that water is moving, so it has momentum. Did you notice, by the way, that when they do their tricks, the hose like stays up in the air, it doesn't just collapse? Why?
because it's full of water.
It's full of water, and the water is moving. And so the water is going up. It's going to take force to change that momentum, right? Newton's second law, written in calculus form, is that the net force is the rate at which momentum is changing. And so you have momentum changing, you can have a net force it's keeping it up there and not just falling down. When it gets up to the person, the water is basically coming up, right? If you're up in the air, it's coming up. And then you have a thing that's going to make the water go down. What's the change in momentum for the water? Just like we did yesterday in class, it was going up with mv, and then it's going down with mv. So the change in momentum is 2 mv for the water. And so that means you have a change in momentum of 2 mv for the person on the flyboard as well. So now I say a change in momentum, you have a net force that's being created in the upward direction, the net force on the water that's pushing it down. And then you have gravity pushing down the person. So the person, if you look at them alone, they have the net force of gravity downward and the net upward force caused by that change in momentum of the water. And so that's what allows them to be up there hovering. And if they make the water go faster, it has more momentum upward, more momentum downward afterward, and so you have a bigger upward force, and that's how you go higher. You make the water go faster. What about the little hand nozzles? What's the point of those? Yeah, it gives you some additional directionality. You know, you can point your hand things that way, you're going to go this way. So it's not just the feet control, they also have some hands. The original one was just feet control. So it was like what they call hoverboards, even though they have nothing in common with a hoverboard from Back to the Future. You know, you control everything just with your balance on that board. That's fundamentally what they're doing there. It's very cool, right? It's the same principle as rocketry, except for you're having actually I should call it jet ski, because most of those weren't jet skis. There was one jet ski there that was doing flips. The rest were like different variety.
Sea-doos.
That's what I call them, yes. But yeah, anyway, that is being used as what is supplying the propellant. So in a normal rocket, the actual physics of calculating what's going on in a normal rocket is, well, it looks really sophisticated, but it's not that hard. And in doing our derivation, because yes, we're going to do a derivation here involving calculus, in doing our derivation, we are going to ignore gravity. Now, of course, gravity exists. It's going to be a constant force that will simply act on top of what we calculate. So in the end, after we're done, we could come back and we could put in gravity if we want to. But for now, we're just making the ridiculous claim. Okay, so here's a rocket far away from any massive object. So there's no gravity to worry about. You start with the rocket of mass m, traveling at speed v through our empty universe. But because it's burning fuel, after some time dt, it will have ejected a certain amount of mass, and that mass has a speed that is speed ve with respect to the rocket. So VE is the speed of ejected material with respect to the rocket. What does it mean when I say with respect to? With respect to means that that's my reference frame. So the rocket always sees the ejected material flying away with speed VE. If you're standing, you're standing in the reference frame where the rocket was initially at rest. Initially, you saw it leave, the ejected material leaves to the right of VE, and the rocket initially had speed of 0 going the other direction. But as soon as you eject some, it's going to have a change in momentum, and it'll start going. Now, I just realized I'm in PowerPoint, and I don't have room to continue in PowerPoint. So I'm going to change from PowerPoint to OneNote so I have room to continue my work. So we have and this has deltas. I'm going to use D's instead of deltas. So I'm going to have dV instead of delta V, dt instead of delta T. What's the difference in delta and D?
Delta and D
Yeah.
change, and that's nothing.
There's one difference. If you use delta, it's an infinitesimal change. Very tiny.
Test.
If you use D, excuse me. If you use D, it's infinitesimal, which means 1 over infinity.
Oh, okay.
So if you use D, it's an infinitesimal change. If you use delta, it's a finite change. So I'm using the D's rather than deltas because we're going to want to do calculus here. Because I said we're in isolation with no gravitational objects, what's the net force on my system of rocket and fuel?
What's the difference between rockets and fuels?
The fuel is the stuff that the rocket is going to burn. And so this stuff here is still fuel. It's no longer part of the rocket. What's the net force on my system of rocket and fuel if it's in isolation?
The sum of force.
Yes, what's the sum of the forces on the rocket and fuel if it's in isolation?
The force of reaction and the force of expulsion.
What's the net?
F react.
When I add them all together, it's going to be 0.
F react minus external.
Right, because it's in isolation, you have nothing external. And this is where, it's in reality, we use a rocket like close to the Earth, and we have a net force that's not 0. So then we have an additional term that we have to worry about there. So we're doing our first calculation here in this assumption that net force in the system is 0. So if I'm going to apply Newton's second law, which I had written before, I'll write it again.
I have a question. Is the F reaction, I guess, is F reaction equal to F expel plus W?
This picture has weight in it, right? So in our calculation, there is no weight. And so if the net force is 0, then that means that those two have to add up to 0. If it's only two forces and they add to 0, that means they must be equal in magnitude, opposite direction. Okay, so the net force is dP dt. So if I want to find dP dt, I'm going to start by saying, what is dP? Well, what's the momentum before? Right, dP is going to be equal to momentum initial, or momentum final minus momentum initial. So what's the momentum I start with? Looking at the left picture. I have a mass of m moving at speed v. What's the momentum? mv. And we'll just consider up to be the positive direction here and not put vector signs on things. So my momentum initial is mv. Now, something that's not as simple was the momentum final.
How are we supposed to do that when our system of interest has increased in size?
It has an astute question. Well, we still have two objects. Well, we now have two objects instead of one. We have the rocket with mass m minus dm because it's lost a little bit of mass, right?
Yeah.
So we have the rocket with mass m minus dm. And what's the speed of the rocket?
V plus dv.
So that's the momentum of one of our two objects. What's the other object then in the second part? The fuel that was ejected. So I'm going to have, and now things, there is a little trick in the signs that we're going to have to take into account at some point. Right now, I would say, okay, so it has massive dm moving downward. So it has massive dm, and it's moving with speed v minus v ejecta. Now, I didn't put a sign there. I should put plus, right? Plus the mass times its speed.
Makes sense, but it's wrong.
I feel like it should be a negative.
Something's kind of busy.
It is something that is going to be a problem. Let's see if you actually have the reason why. So what was your reason why you think it's going to be a negative?
Because you said something about fuel. You gave some idea that it was negative, like going down or something.
Okay. What about you?
It's all a theory about how, you're losing fuel, which is losing mass, and so it wouldn't be negative in a way, because you're, from momentum final, you subtract momentum from the fuel.
Well, and everything appears right here, right? You have the mass that's left in the rocket is m minus dm, where dm is a positive value. So you have less mass, and the speed of the rocket is v plus dv, it's going faster. And then you have dm, positive mass here, and then you have the speed at which it's moving is slower by ve. And so like if we started with v equals 0, this would be a negative. If we start with v as positive, this is still probably going to be positive, but it's smaller than what we had before. So this is what we have for momentum final, or expanding this out, we'll get to the issue I was referring to. mv plus mdv minus vdm minus dmdv plus vdm minus vedm. So there I've expanded the terms.
Your velocity and the change of mass disappears. That's the issue.
So I'm going to have this and this add to 0, right? And that's all I can do right now. So my momentum final is mv plus mdv minus vedm minus dmdv. And so my change in momentum is momentum final, so the thing I just wrote, minus the momentum initial, so minus mv. So these subtract out. So I'm left with dp is equal to mdv minus VE dm minus dm dV. Now, if you look at this, there's one thing that might cause you pause. What thing in that might cause you pause? One of these things is not like the other.
The D. Never mind. The VE.
The last term has two D's, dm times dV. But what did I say about D? What does D mean?
Change it.
It's an infinitesimal change in. So if I have an infinitesimal change in M times an infinitesimal change in V,
That's pretty much zero.
that's pretty much zero. And so because the other ones are a finite times an infinitesimal, this is infinitesimal squared, this term here is approximately zero.
Is that basically dm divided by dt? Is that what you're saying?
No, it's dm times dV.
But the d's are infinity.
The D's are 1 over infinity.
Infinitesimal small
Yeah.
change in time. Okay.
Yes. So this is one infinitesimal times another infinitesimal, which means it's on the order of 1 over infinity squared in size. And the other ones are on the order of 1 over infinity.
It's a bigger infinity about
So a bigger 1 over, yeah. Now, going back to where we started, if there's no weight, the net force is 0, so dp dt is 0. Now, I didn't put dp dt, I just did dp here. But if dp dt is 0, then this has to equal 0. So I have mdv minus ve dm equals 0. And when you look at this, you now have an equation that you have enough differential equations experience to solve, even though none of you have taken differential equations to that class. Because how many variables do I have here? 2, m and v. What did we learn to do the first day of class this semester when we have a differential equation with 2 variables like this? We first have to separate the variables. And so first I'm going to move the VE dm to the other side of the equal sign. And then to separate variables, I'm going to need to divide both sides by m. Divide both sides by m so that I only have m on the right side and only v on the left side. Now you might ask, what about VE? Well, I could divide by VE, but VE is a constant. It's not a variable. That was the speed of the ejected material, not the speed of the rocket. So now, the final thing here, well, the penultimate thing, the next to final thing. The dm, everything made sense, but I said there was a problem. Remember that? It all made logical sense. But the thing is, dm
equal each other.
dm is amount of mass that's leaving. Whereas m is the amount of mass that remains. I need to flip the sign on the dm at this point to make it an additional dm. Even though there is no addition of dm to it, I need to flip its sign. That's where there is the apparent problem.
dm is how much mass how much fuel you're losing, basically.
Well, m is how much the mass of the rocket and the remaining fuel of the rocket is at any moment.
Okay.
And dm was how much mass we're losing. But in calculus, we need dm to be how much we're increasing. And so that's why that red minus sign is put in there. Because it's the calculus definition of dm versus how we defined it initially. So now I integrate both sides independently. Integrate from the starting speed to the final speed. Integrate from the starting mass to the final mass. And I have V final minus V initial is equal to minus VE natural log of M final over M initial. Well, this isn't very hard, now is it? What's the final speed of the rocket? I'll add V0 to both sides. And notice it's minus. Is the rocket going to slow down over time?
Yes, no.
It should speed up if it's still burning.
Yeah, it's still
Oh, well, I thought you meant like the finals.
Yeah, after you stop burning, if there is something like, it's hitting atmosphere, it'll slow down. If there's no atmosphere and there's no external forces of any kind, you just keep cruising at constant speed. But minus natural log of mf over m initial is equal to natural log of m initial over mf. So I'm going to do that to get rid of the minus sign, because the minus sign makes you think it's doing something different. And there's the equation that tells me the speed of my rocket in isolation as a function of its starting speed, its starting mass, and its ending mass. Now keep in mind, the rocket's starting mass is always bigger than its ending mass, because it ejected mass as it was burning. So that means that the natural log of MO over or M0 over MF is always a positive value. Hence, it's going to be going faster. So this is the principle of how a rocket works. Now, like I said, we did this to the exclusion of gravity. If we included gravity, we would have to have a gravitational term in this. But I want to make sure we can understand the concept of how the rocket works without having a complication to make life harder for us. So when I'm doing something like this, if I want to know about the speed of the rocket, I need to know how fast the material is being ejected and how much fuel it has. If I want to make my rocket reach a higher ultimate speed, then I need to make VE larger, right? Because the bigger VE is, the faster it's going to go. And I need to make M0 over MF as large as I can. So once again, that comes back to what Randy knew when we started, that it's mostly fuel. Because if it's mostly fuel, that ratio of M initial over M final might be 2 or 3. And so you're getting a very big result from that natural log compared to if the fuel made up 1/3 of its mass, you'd have a pretty small amount for that natural log term. So that's why you have mass as a big proportion. The reason you have stages in rockets is because you have one stage that burns and you get the natural log of the mass that started for that stage, the mass that ends for that stage. Then you eject the casing, so you eject some mass, and then you burn the rest of the fuel with less mass, so you get bigger proportional boost from the second and third stages than you did from the first stage if they're all equal.
Because you need more boost to meet the hemisphere in certain places.
Well, say you're trying to take something really heavy up. If you're taking something really heavy, you're going to have because gravity is now involved, right, to get it away from Earth. If you're taking up something heavy, you're going to have more energy delivered, if you will. And so you're going to have to burn more fuel. But if you can limit how much weight you're lifting, then you're going to have an easier time. So you make it stages, so you burn this much, and then you drop the metal that was holding that in place, so you have less that remains. Now with rockets, what we measure with rockets is the thrust. And the thrust is the speed of the ejected material times dm dt. Now, if we came back to my differential equation, where was my differential equation? To this right here, this equation that I put a box around. Well, that was what the equation was. If I divide both sides by t, then this side here is the thrust. And you can see it's units of mass times dv dt acceleration. That's telling me what the net force is. And of course, in reality, I would have to have g associated here as well. Because my net force would be this minus mg. And so that's where things would be different in the actual derivation is I would have to have mdv dt equals ve dm dt plus, or minus gm.
So thrust is measured in joules.
No, that's units of newtons.
Oh, you're right.
And so at this point, we could go ahead and we could say, now what happens if we had gravity? So with gravity, all of the work I did would still be the same, except for I have minus mg. And so then I still have to divide everything by m. And so those will cancel, and I have over m here. But then I have the dt thing. And when I multiply by dt, if I multiply everything by dt, I'm going to have something like that. And I have one term that's just a function of v, one is a function of m, one's a function of t. And well, things just got a little harder, right? So that's why we didn't do it that way. Now, in terms of problems you might encounter, I am not going to ask you to do this derivation just because you make one little mistake and you feel like you're, somewhere in third grade when everybody else is in college, right? It's too easy to forget one little thing. What you do need to be able to do is to simply be able to apply, where's the equation? Apply this equation for no gravity. I didn't work it out, so I don't have the equation with gravity completed, but be able to apply that one for no gravity for, a rocket. So it's just putting numbers in. It's not actually using calculus, but we had to use calculus to get there. That's why it's here. So any questions about the rocketry thing?
It's easier when we're following the teacher.
That is so true. Not so much of a question, but so true. This is another picture to show how it works and some of the derivation there. And then here is the actual work that we did. So we did all of it, and we ended up, that's the equation we ended up with, right? Yeah. So these here are just, in case you were to have been lost in my work, I have all the words going with it so you can read it out in something that is clear in reading. Question, David?
That equation assumes that our initial velocity is 0.
Yes, that assumes the initial velocity is 0, right. And here is assuming that it's, or not assuming it's 0. Okay, that.
What's that?
What was that?
VE. What is that?
Okay, gentlemen, what was VE?
The speed of the expelled material.
The speed of the expelled material with respect to the rocket.
Yes.
All right, that is where I'm done for the day. Is there anything else I should do?
Cancel that.
No, we won't be doing that. So sorry. Were you able to take it through that quiz?
I did.
Okay.
If it's on Moodle, I can handle.
Okay.
But everywhere else is no go.
All right. Well, we're done early, which, we only have 4.5 units for this class. So on average, we should be skipping every other week, right?
What? 4.5 what?
4.5 units of credit for this class.
I mean, I'd be okay if we did that.
Surprisingly enough,